So today I'm happy to be talking a little bit about one of my favorite techniques in the field of microscopy, and that's FIB-SEM tomography, really looking at a slice-by-slice breakdown of material science in the micro scale. So today my webinar is going to be broken up into four main components, the first of which is a little bit of an investigation as to what FIB-SEM can do for you. So what are you actually able to image using the technique? In part two, we're going to dive into the microscope, look a little bit at how we can set up a FIB-SEM tomography acquisition. Part three is after we've come out of the microscope, what can we do with our data? And part four is a short introduction to some of the FIBs that we have available at CCEM and some of the modalities that we're able to couple with that FIB-SEM tomography technique. So part one, what can FIB-SEM do for you? And with this, I actually don't want to start in the microscope. I want to start in the kitchen. With this question of what if we have this structure that has a complex morphology on its inside. So something like cabbage, for instance. On the inside of this cabbage, it has a number of layers and a very unique sort of macro structure. And so if we wanted to view the inside layers of this cabbage, we could use a knife to cut away a thin slice of cabbage. And then we could look at the newly exposed surface of that cabbage. And then if we wanted to view a little bit deeper into the cabbage, we could again use a knife to cut away another piece and then look at the newly exposed surface again. And then we could repeat this over and over and over again until the entire cabbage has been cut away. And we have this digital image stack representing what was left of the cabbage. Now, in the microscope, things are obviously a little bit different. Instead of working with a cabbage, we're going to work with your sample of interest, whether that's a semiconductor material, whether that's a biomaterial, whether that's a thin film, you name it. Instead of using our phone camera to digitally log these images, we're going to use the optics from a scanning electron microscope. And instead of a knife to do slice-by-slice removal of material, we're instead going to be using a focused beam of ions, whether that's from a gallium source, a xenon source, or any other number of sources that are available on the market. It's also important to note in this cabbage example that FIB-SEM tomography is inherently a destructive technique, meaning that material we cut away can't actually be used to reassemble the cabbage to its initial form, its initial spherical form. And instead, we get left with remnants of sliced away material. So although maybe we can make a bowl of coleslaw, we actually cannot reassemble that cabbage into its initial form. Now, if we look at one slice of this cabbage, for instance, one image, we have its representation in space, depending on where that slice was taken. So if we take our series of images from these cabbages, we align them in such a way that they are in order in the slice number that they were sampled from. We can actually build a digital reconstruction of our cabbage, even though it has been milled away. It's been destroyed completely by this FIB-SEM tomography process. And so in our 2D images, each pixel in this image now has a thickness associated with it or a depth associated with it, meaning that we've gone from a 2D pixel to a 3D voxel. And if we have an array of 3D voxels, we can then build a 3D volume that represents our initial shape. And depending on the thickness of slices that we acquired during the tomography acquisition, we can have thick slices, we can have thin slices, we can have this Goldilocks principle somewhere in between slices. That's going to dictate some of the imaging resolution that we have available in our 3D volume. And I'll talk a little bit about the importance of choosing the proper slice thickness a little bit later on. But for now, one of the main questions we get when we run FIB-SEM tomography acquisitions is, well, what size cabbage can I analyze in the microscope? How big of a volume can I get with doing FIB-SEM tomography? And what resolution can I achieve using that volume? And so I've put together a table here of various volume sizes and voxel sizes that we can use in the microscope. So if we're looking at smaller volumes, typically on the order of about 5 micron by 5 micron by 5 micron, all the way up to maybe 50 micron by 50 micron by 50 micron. That tends to be suitable for FIB using gallium-based systems. And with these smallest volumes, we can go down to a voxel size of about 3 to 4 nanometers. And we can use that to image features that are larger than 30 nanometers in size. Your mileage may vary a bit depending on the exact sample that we're working with. And then these intermediate volumes, maybe a 50 micron by 50 micron by 50 micron volume, we can look at features that are roughly 200 nanometers in size or larger. We can use a voxel size in the order of 15 to 50 nanometers. However, if we want to probe larger 3D imaging volumes, we can also use our plasma FIB that we have available here at McMaster at the CCEM to probe these larger volumes to achieve a larger voxel size and look at larger features still in the structure. If we want to look at features that are smaller than, let's say, 20 nanometers, perhaps we want to consider another technique, something like electron tomography that we can use for 3D imaging using the TEM. Or if we're working at very large features, we need very large volumes. Maybe we want to consider using microcomputed tomography or XCT-based methods instead. But FIB-SEM fills an important niche between these two length scales to be able to do important 3D characterization of our material systems. And it's important to note that these are quite time intensive, these acquisitions. If we're looking at small volumes, it can be as little as 24 hours of automated FIB-SEM tomography acquisition. But if we're looking at large volumes, that could often take up to 14 days or even more of automated acquisition to be able to achieve a volume on the order of 100 microns or larger. And it's important to note here that these voxel sizes, as they decrease, as we get smaller at voxels, we get higher fidelity of the actual object that we're imaging, but that takes longer time to acquire. If we're comfortable working with a larger voxel size, we get worse imaging fidelity, but the tomography acquisition time tends to be lower. So based on this, how do we actually choose a voxel size and a volume size for our objects? And the honest answer is it depends on your sample, and it depends on the size of features in your sample. So I've prepared this graphic that shows a few examples of what a sphere looks like if it's represented by a different number of voxels in the voxel cloud. So if we're working with features that are 700 voxels in diameter, let's say, the sphere in 3D here actually looks quite smooth. We have excellent resolving power, and it's really true to shape. However, as we decrease and our features get smaller, fewer and fewer in voxel number, for instance, we actually deviate further and further from the actual shape, meaning that we have lower fidelity of our imaging and lower resolving power in the 3D volume. So if we're imaging features that are 200 nanometers in diameter, let's say, and we're comfortable working with a voxel size of 10 nanometers, we can expect the sphere to look something like this. Same thing, if we're working with voxels on the order of 10 nanometers and our features are 400 nanometers in size, we can work with this. If we're 7 microns in size, we can work with this. But if we're only 20 nanometers in size, our features are going to look like this. So the trade-off between voxel size and feature size is entirely dependent on your sample. And we're happy to help inform that as well if you're able to help describe that sample to us. So what are we able to do with FIB-SEM? One of the first thing that jumps out is we can achieve visually appealing 3D renderings of your material system. So if you're looking for a journal cover, it's a great example of a real microscopy technique that we can use to generate beautiful images. We can use this for feature quantification. So whether that's things like grain analysis, porosity measurements, looking at thickness deviations, or the orientation of various objects, we're able to do that in 3D. And that quantification is always going to be more accurate in 3D than it is in 2D. If we consider the columnar structure like this, if we're looking at the wrong two different planes of section, our features appear completely different. But if we're capturing this in 3D, we get a full idea of what those grains might look like. Perhaps we want to generate FEA meshes that are inspired by real-world data. With an imaging volume of your sample, we can actually use that to inform things like grain size, porosity fraction that are important for your simulations. Or we can couple the 3D imaging with 3D EDX or EBST technique to actually get 3D maps of chemical composition or crystallographic orientation data. And so let's look at a quick case study of what we've done recently in the CCEM. So this is a sample from a meteorite, and we can actually see the 3D imaging volume here. These bright particles and particle aggregates that we're seeing are iron-based compounds. And the overall width of this volume is about 250 microns in size. So if we can segment out some of those bright features and zoom in on the segmentation, we can really get an idea of what's happening into the lower end of the microscale to look at how these are packing together to form 3D structures. As well, if we want to do quantification, we can take a sub-volume of this 3D volume. we can segment out each of these little particles individually, and we can get maps of their the porosity fraction. We can get maps of the size of the particles. So in this case, each of these little spheres has an average diameter of about 800 nanometers. And as well, for this particular run, we've actually been able to couple this with 3D EDX. So we're actually able to get spatial maps of chemical composition throughout the structure of that geological sample. So we can look at where iron is preferentially located. We can look at where carbon is deficient. We can look at sulfides in the 3D volume, all with excellent spatial resolution. So now that we have a good understanding of what FIBSEM is able to do, I want to jump into the microscope for a minute to look at how we actually set up a FIBSEM tomography run and what's going on inside the chamber. And to do that, perhaps it's best I give a quick primer on ion generation interactions. So the most common type of ion source that we're using to do our milling is a liquid metal ion source, most commonly using pure gallium metal as a source. That gallium is heated to liquid temperatures, roughly 30 degrees, and it wets the tip of a tungsten filament that's in the microscope. Under a strong electric field, that liquid gallium is pulled into what's called a Taylor cone. And if we apply electrostatic lenses underneath that, we're actually getting field emission from this Taylor cone, emitting singular gallium ions that we can use to do our cutting. And these electrostatic lenses focus this into a precise beam that we can use to do fine, controlled milling operations. These incident ions then come in towards our sample of interest, and they're actually ablating away atoms within the substrate. So these incident ions have a specific momentum associated with them. They actually break the atomic bonds as they're colliding with the substrate material, and we get the result is that milling or sputtering effect when the ion beam is rastering over the sample surface. And if you want more information about FIB as a technique and as a whole, I recommend checking out 2 of our previous webinars from Travis Casagrande about FIB applications and introduction as well. So if we're looking at the FIB chamber, this is our Helios 5 UC as an example. It's quite a complex system. Up at the top here, we have the electron column. This is where electrons are generated and pointed towards the sample. This electron beam is able to do imaging, but as well, it can be coupled with the gas injection system to do a low damage type of deposition of low purity tungsten, platinum, or carbon. Over here on the left, what we can see is our ion column. So in this instance, it's generating gallium ions that we're aiming at the sample. And we can use that to do milling, as I just mentioned. And this is offset from the electron column by about 52 or 54 degrees. As well, our incident ions are actually producing secondary electrons as well, although it's damaging the sample. So we can generate an electron image using our incident beam of ions. And as well, we can use these ions to do, again, deposition of tungsten, platinum, or carbon on our sample surface. As well, there's a number of accessories that we can couple here on the side of the microscope, things like a micromanipulator, things like specific detectors, and things like the actual gas injection needles themselves. But if we want to look inside the chamber, what we can see is that up here at the top, we have our electron column pole piece. So electrons are going to be flowing out of that towards our sample. Over here on the right, we have our focused ion beam pole piece. So in this case, gallium or xenon ions are going to be flowing out of this towards our sample. And these are going to be at coincidence, meaning ideally they're pointing at the exact same location on the sample. We have our sample stage where the sample is going to be resting. And then we have our tilt axis. So we can rock back and forth from a milling position to an imaging position, and so on and so forth, back and forth until we're happy with our run. And so for FIBSEM tomography, there's 2 types of specific tomography. There's edge tomography, which is available on our Thermo Fisher FIB systems. And for that, we need a feature of interest that is located on the very edge of our sample. So we need a 90-degree cliff face here. And when we do our actual imaging, the electrons are going to be coming in and imaging the cliff face that's actually not visible here in this isometric view. They're going to be coming in that way, and our ions are going to be coming from north to south on this image, so actually cutting away that cliff face. Alternatively, if we don't have a feature of interest that's exposed on the side of our sample, we can cut the sample to the region of interest, roughly within 30 microns or so of that feature, and we can do that in-house using techniques like laser FIB, or we can use traditional mechanical cutting means as well. Second type of tomography is what's called an interior tomography. and this is available in our Thermo Fisher and our Zeiss FIB systems here at CCEM, where the feature of interest is located somewhere in the center of the sample, and we have to generate our own 90-degree cliff face, where the incident electrons are actually going to be coming in at an angle, and then we can use image analysis operations to rescale the image as needed to its appropriate size. And so for these interior tomographies, where the feature is in the middle of the sample actually does not move over the course of the tomography run, or only minor movements are possible between the milling and imaging positions. So if we're doing our milling, our sample is oriented like this. Our ions are coming out of our ion column, and they're milling our sample. We can then switch to SEM imaging without movement of the sample to take a picture at this exact same stage position. We go back to FIB milling, we go back to SEM imaging, and so on and so forth across hundreds or thousands of slices. This tends to be a bit faster than edge tomography because we don't have to wait for the stage to move back and forth. So for edge tomographies, the sample actually does move between these imaging and milling positions. We actually tilt the stage by about 45 degrees to point the sample towards the electron gun. So in our milling stage, our cutting stage of FIB-SEM tomography, we're ablating material, and then we rotate the stage by about 40 degrees so that this is normal to the electron column. We can actually take an image like this, then we rotate our stage back to the milling position, back to the imaging position, back to the milling position, and so forth across hundreds or thousands of slices. So how do we set up one of these interior tomographies, if that's what we want to do? So over here is a schematic that's going to be developing, that's going to show what we can see in the FIB view, what we can see with FIB imaging. So the first step in preparing an interior tomography is to deposit this protective capping layer over top of your region of interest using the gas injection system and either the electron beam or the ion beam. We have gaseous precursors available that are able to make low purity carbon, tungsten, or platinum deposits, depending on what material system you're working with. And typically we want this to be at least 2 to 3 microns in thickness. And this is going to protect our region of interest from that repetitive ion beam exposure. We're only irradiating the areas we want to, but damage can accumulate over time if we're not being careful about how we protect our surface. After that, in our Thermo Fisher systems, we actually want to deposit a second protective layer right next to that region of interest, again, using the gas injection system. Again, we're targeting a thickness here of about 3 microns. And we want this to be separated from our primary deposit by about 4 to 5 microns. And this is going to be important because this is going to be a marker that the ion beam uses to track its position over time. It's what's called a fiducial marker. So it knows where it's milling for each consecutive slice. Without this marker, our FIB beam does not know where to cut, and it's actually impossible to do FIB tomography. So these type of fiducials are important to prepare properly to be able to mill in the correct position. Once we have our 2 deposits down, we're going to retract that gas injection system. And we're going to use the ion beam to mill away excess material on both the right and left sides of our region of interest. And this is going to help prevent shadowing effect of our electron images during the actual image acquisition portion of the tomography run, meaning that electrons generated from the electron beam at higher depth have a better line of sight to the detector, and that eliminates shadowing effects that we can see in our images. As well, it creates a cavity where milled away material can actually escape to without contaminating our previously nicely cut surface, and it won't obstruct our volume of interest. And for best practices, each of these 2 trenches on the left and right sides should be about 1/3 to 1/4 the width of our overall tomography volume, that initial deposit. After this, we're going to use the ion beam to mill away excess material in front of the region of interest. So this is the step that's actually creating that 90-degree cliff face. And it's going to do so by creating a sloped surface that's going to be at its highest depth when you're at that 90-degree cliff face, so at the edge of this deposit that we've put down. And it's going to be level with the sample surface towards its bottom. And again, this provides a pathway for the electron beam to actually see the milled cross-section. It's going to prevent shadowing of the electron images again. Again, signal generated at depth can escape to the detector so we can actually detect it. And in general, the length of this trench, the Y direction in this case, should be about 2 times depth of one of your slices. And in practice, it's best to often work using a graded series of currents. So you want your first iteration of this to be at high current. And as you get closer and closer to the actual volume of interest, you want to reduce your ion current step by step to get a nicer cross section. Next, we're going to create a recognizable fiducial shape on that secondary pad that's going to allow that ion beam to actually map its position. Generally, something with corners, like this little X shape, tends to work quite well. The ion beam will take the image, it will recognize those markings, and it will know where to increment the next slice milling position to. And we want to make sure that that is milled throughout the entirety of this secondary deposit. And it's actually milling into the sample slightly as well. Alternatively, if we're working on a Zeiss FIB system, we actually don't need that secondary deposit with the X on top. We can implement a different type of fiducial tracking where we have a carbon layer deposition, these two angled layers of carbon that are in the primary capping layer and then coated with tungsten on top. And that is useful for both SEM alignment and FIB positioning as well. So we can use, you can use these markings for both. And what does this look like in the microscope? So on one of our Zeiss FIBs, for instance, this is an ROI that's a region of interest that's set up in the two views. So what we have on the left here is what the FIB sees when we're ready to acquire tomography. And on here on the right is what the SEM sees right before we're about to acquire tomography. And if we zoom in on this SEM view, we can see these little carbon deposits that I just mentioned that are going to be important for our fiducial marker for both imaging and for milling. In a Thermo Fisher FIB, what we can see is that if we have a tomography volume that's ready to go, like this one on the left, we can see our fiducial marker, we can see our primary deposit, and we're ready to begin imaging. In the SEM view, we can see the materials cut away, we can actually see the exposed cross-section. And what it looks like after tomography in the FIB view is we can see that much of this material has actually been milled away, meaning that we have a significant image stack that we're able to reconstruct in post-processing. If we're preparing an edge tomography, the workflow is very, very similar. It's just that this primary deposit has to be placed as close to the edge of the sample as possible, and we're only removing a very small amount of material in front of that volume of interest. So again, we deposit the protective capping layer, we deposit the fiducial pad, we mill trenches on either side, we remove that small trench in front of the region of interest to expose that cross-sectional face, and then we mill our fiducial for that ion beam tracking. For large volume tomographies, so we're looking at things that are maybe 100 microns or larger, where we can have a significant amount of material to remove or a substantial amount of shadowing because these are quite deep. We can actually do lift outs. So we're able to lift out our volume of interest and attach it to something that's a bit more conducive for 3D imaging. So something like a custom grid, for example, that we can use, that we can prepare in-house using our laser FIB system. We can lift out the sample and place it on the central post of this grid, where there's no material on the left, no material on the right, no material behind, and no material in front, meaning that electrons are able to get to the detector easier, as well as ablated material is less likely to contaminate your nicely milled surface. So we can lift out your volume of interest from your sample. In this case, maybe it's something as large as 500 microns. And we can weld it to that middle post on one of these custom TEM grids where those artifacts are going to be much less consequential and we'll get a better overall 3D volume. So one of the questions we often get to is what parameters do I need to work with if I'm setting up a FIB-SEM tomography run? And one of the important things to think about is what ion beam current you're going to use. Typically, the slicing is done with an ion beam voltage of 30 kilovolts. But this current is something that we're able to select based on our own preferences. So with lower currents, we get lower probe diameters, which means we get higher milling precision, but that takes longer to acquire, longer to perform the slicing operation. We have fewer incident ions, which means we have to expose for longer times to achieve the same depth. Alternatively, if we use high currents, we have a higher probe diameter, meaning we have slightly less milling precision, but we have overall shorter acquisition times. And I have a table here of some recommended ion currents that we can use depending on our voxel size. So typically, if we want to push for higher resolution, we want to use lower ion currents. if we're okay with a larger voxel size, then maybe we can use a higher ion current for that. Now, each of these runs, as I mentioned, can take 1 day or they can take up to 2 weeks. So as a result of that, the microscope conditions are actually changing over time. So we need to correct for things like the focus, things like the brightness. And so how often should we do that using the automated software? And again, these are my recommendations. It's going to vary depending on what sample you're looking at, but perhaps an auto contrast brightness adjustment every 5 slices is suitable. An autofocus and auto stigmation operations, maybe every 5 to 10 slices might be suitable depending on your volume of interest. Things like source tilt and lens alignment, we need to do much less frequently, depending on the stability of the microscope at that time. And some benchmarks for a single slice acquisition. Typically, we want the milling step to take between 10 seconds and 60 seconds, and the imaging step for each slice to take between 30 seconds and 90 seconds. Again, these are ballpark figures. The exact values are going to depend on what features you need to see in your sample, but it's important to provide some recommendations to get us started. Another thing to consider too is what electron beam accelerating voltage or landing energy that we're actually using to do the imaging steps. So if we use a higher kV, that's going to generate a larger interaction volume, meaning we're not getting as much information near the surface as we might hope. We're actually probing a fairly large depth of material. If we're at 5 or 10 kV for a carbon-based sample, for instance, we might be probing as much as 50 or 100 nanometers, which means instead of imaging 1 slice, you're actually imaging 5 or 10 slices in depth. But if we use lower kV, we can actually reduce that size of the interaction volume. Maybe if we're using 1 to 2 kV, for instance, we're only imaging about 10 nanometers in depth. So we have a lot more surface sensitivity as we reduce the accelerating voltage of that electron beam. And again, it's going to depend on what your slice thickness is. But if we need to couple this with something like EDX, then we need to use higher accelerating voltages. So there is a bit of a trade-off there. As well, the slice thickness, this is something we get to choose when we set up our tomography runs. And when possible, we want to select our slice thickness to match the size of the pixel in the image in both the X and Y dimensions. And this is what's called an isotropic voxel, when our pixels are the same dimension in X, Y, and Z. So 5 nanometer by 5 nanometer by 5 nanometer voxels, for instance. As well, one additional consideration when we're doing interior tomographies is that we should have tilt correction enabled in the microscope. So if we're imaging at a tilt angle, which we typically are doing in these types of interior tomographies, and we acquire an image that looks a little bit like this, here I'm at a tilt angle of about 30 degrees, and we want to take a measurement. It looks like it's only about 8 microns in this particular instance. But if we enable the tilt correction in the microscope, its true depth is actually 16 microns. So some of our features can be distorted if we don't have this tilt correction feature enabled. And that Y scaling factor, that digital correction, is a function of our specimen tilt angle. And the exact formula here is here. It's 1 over the sine of the specimen tilt angle. So in this case, if we're at a tilt of 30 degrees, the image is actually scaled in the Y direction by a factor of 2. And that's what our true cross-section will actually look like. And this is best applied before you acquire the images. You can scale them up in post-processing if you need to, but the easiest way to do this is to let the microscope do the work for you. Now I want to talk a little bit about 2 types of artifacts that we might commonly see in FIB-SEM tomography. And if we have a multi-phase or a composite material, what we can often find is that we get these curtaining artifacts because they appear quite like a theater curtain might, appearing on our newly milled cross-section. And that's compounded by a forward scattering effect of ions during the milling operation. And so if we're doing a single milling direction, this can propagate over time. And so there's actually a feature enabled on some of our microscopes, which is called a rocking mill, which means between slices, we're actually doing FIB milling in one direction. And then we're offsetting the milling direction by a small amount to mill at a slightly different direction. And if we alternate these back and forth, what we can get is a cross-section that instead of looking like we have over here on the left, we can get a much smoother cross-section, meaning we can actually see our features much easier. If rocking mill is something that's not possible on our sample for some reason, maybe the microscope doesn't have it enabled, We can also achieve a similar effect by just using a lower ion beam current to do our milling operations, and that should also get us a smoother cross-section. The second artifact I want to talk about is charging. And whether you're using biological, geological sample, maybe you have something that's oxides, based on oxides, it's non-conductive specimens where we start to see this the most, where we have an accumulation of charge, electrons that we're putting in that are unable to escape the specimen. And the resulting image can look a little bit like this. So this is an example of one of my FIB-SEM tomography slices. Over here on the left, we have a calcium carbonate mineral within an eggshell. And over here on the right, we have the organic fibers of the eggshell itself. And if we look within the calcium carbonate mineral, we can see this bright white phase that is not conducive to actually resolving how these fibers are interdigitating with that mineral phase. So if we see these types of charging artifacts, there's a few things that we can do in our tomography setup to reduce these charging artifacts. And the first of which is to improve the connection to ground by sputtering the entire sample with a conductive material before we put it in a microscope. So if it's more conductive, these electrons are more likely to escape to ground and we get less charge accumulation. We can also reduce the number of electrons coming into the sample by lowering the current of the electron beam. If we have fewer electrons coming in, we get less charge accumulation and we get less of this charging artifact. We can adjust the electron emission coefficients by changing the accelerating voltage of our electron beam. Typically, we want to lower this, but it does depend on the material system. So we want to balance the number of electrons that are coming into our sample and going out of our sample to achieve less charge accumulation. Typically, we want to work with a KV around 1 to 2, but again, it's sample dependent. We can reduce the number of incident electrons by lowering the dwell time of the electron beam. Again, fewer electrons provides less charge accumulation in your specimen. Or we can use frame averaging and line averaging approaches to allow some time for charge dissipation before we scan each pixel over and over again. That tends to work quite well to mitigate these charging artifacts. And if we do all of these, instead of having these big, ugly white regions charging in our specimen, we can actually achieve something that is a bit more true to form, where we can actually see how these organic fibers are interdigitating with that calcium carbonate mineral. Okay, so we've set up our run, we've set up our automated acquisition, we've got our data, now what? So in the data reconstruction, there's a number of software packages that you could use to actually render your data and take measurements. So there's subscription-based software available for industry use. So things like Dragonfly 3D World, for instance, or Amira Aviso offered by Thermo Fisher are available. If you're an academic user, Dragonfly 3D World is free for academic use through Object Research Systems, or you can use any number of open source softwares. So things like 3D Slicer, things like Fiji have plugins to be able to handle these 3D data sets. Here at CCM, we have Dragonfly 3D World available for both industry projects and workstations available for academic use as well. So if you have a 3D FIB-SEM tomography data set you're trying to work with, you're welcome to use our computing resources to help process that data as well. And so if we've acquired our slices, I want to introduce now what's called the banana cucumber problem. And that's because if we look at these two shapes, we can see that they have very different morphologies. Our cucumber is very linear in shape, whereas that banana is actually very curved in shape. But if we look at a single 2D cross-section through each of these, it is circular in shape. So if we have this arrangement of circles, how do we know whether these circles are arranged in that linear form or whether they form that banana type shape? And the answer is with fiducial markers and using proper slice registration protocols. If we want to do something that's called fiducial-based registration, and this is typically with volumes that are not rich in information in a single image, what we can do is right next to that tomography volume, when we're preparing the site, we can add a marker. In this case, I've added a small x in the case of this eggshell, for instance. And this is going to be in the exact same position, no matter which slice we're acquiring in that 3D volume. It does not move, meaning that if we use this to position each image in the stack, and we position the images such that this X is in the same spot, but our Z is varying, we'll get a true to size 3D volume that is properly registered and the slices are properly aligned with one another in 3D. And this can be done as a post-process slice positioning algorithm, but we can also have steps that help with this in the microscope as well. Or the second thing we can do is that if our imaging plane has enough cucumbers or enough bananas present in the slice, it's feature rich, and these are oriented with a variety of 3D orientations, we can actually extract information from the image itself that we can use to do real-time registration in the microscope, as well as applying algorithms to refine this in post-processing. But the important thing is that no matter which of these two techniques you're doing, one of the first image processing operations when you get out of the microscope should be to do some form of slice registration. And I'll show an example of that here. But this is going to be pivotal in determining whether we're looking at a banana or a cucumber, or we're not hallucinating and seeing something that's curvature that might not actually be there, or linearity that might not actually be there in our data. So if we look at the example, this is an image stack acquired from that same meteorite that I showed earlier. This is one of our 2D images of these fused spheres that we have in the imaging plane. But when we reconstruct our 3D volume, that reconstructed plane is not very rich in features. We cannot resolve any shapes in this reconstructed plane. And that's because our slices are not properly aligned in 3D. So if I apply an SSD slice registration algorithm, again, an image matching based algorithm, based on the information common in all these slices, we can see that our reconstructed plane is now much more rich in features. We can actually see that these spheres are present in 3D. We can see that this dark shape in the middle is persisting in the XZ and YZ planes as well. And if we look closely on the edges of this reconstruction, we can actually see how much each slice has shifted in the XY position by in that slice registration stage of post-processing. As well as an optional step, after we've done this form of slice registration, we can do a noise reduction technique using something like Gaussian smoothing. So if we have an image that has this type of salt and pepper type noise, or impulse noise as it's called in the imaging world, we can apply smoothing operations to be able to normalize the gray levels to make our life easier in segmentation and actually more clearly delineate the boundaries of our features of interest. So now we've got our data out of the microscope. Our data is properly aligned. We've filtered the data to lower some noise. It's time to talk about segmentation of our features. And when we're looking at segmentation, there's two types of segmentation that I want to discuss. The first of which is called semantic segmentation. So every object of the same type is grouped into what's called a class. So if we're looking at this image of trees, for example, that semantic segmentation would be an examination of all the trees in the forest. The second type is what's called instance segmentation, where individual objects within that class are separated into unique labels. So if we're looking at the class of trees, we can further partition our data set and specifically look at this tree. And so if we're looking at the semantic segmentation, trees, we can answer numerical questions and quantitate our data set. So we can ask questions like, how dense is the forest? So if we want porosity measurements, maybe the semantic segmentation is sufficient. How much land does the forest occupy? Again, that's something we can do by grouping all objects into the same class. But with the semantic segmentation, we can't answer questions about individual trees in the forest. So we can't say how many trees are there. We can't tell how tall is the average tree, and we can't tell how far apart these trees are spaced. So if we want things like statistical measurements, we need to be able to take this semantic segmentation of our 3D data and partition it into an instance segmentation. These are some examples of what 3D renderings of your data might look like in semantic and instance forms of segmentation. And we have some tricks that are able to get us from semantic to instance. So semantic, everything is grouped into the same class. Instance, each entity in that semantic class is separated into its own unique label. So oftentimes to achieve that instance segmentation, to be able to do statistics, we need to acquire the semantic segmentation first. And there's a few ways that we could do that. So if we're looking at a 2D slice, for instance, we can classify all features with a similar gray level into a shared class and segment features that way. That's typically very easy to do, but oftentimes real world data is does not behave in the way that we want it to, whether there's brightness contrast variations or whether we have two features that have the same gray level. So the second thing we can do is to manually create a few examples of training data. So we can paint training data onto the cell, for instance, if we want to delineate the cell membrane from the nuclear membrane here. We can paint a few slices and train a neural network to actually segment our images for us. This tends to be more difficult, but the result is much more robust when we have complicated 3D data. And then if we apply that to the full image stack, what we get is a full 3D volume where all the slices have the plasma membrane and the nuclear membrane segmented appropriately. And if we want to jump from an instance segmentation to, if we want to jump from a semantic segmentation, to an instance segmentation, we can use techniques like the watershed transform that help us split that class into individual labels. But I won't dive too deep into that. But if you want specifics on how we could perform the watershed transform, for instance, you can reach out to me after the webinar. Now, I've talked a little bit about how we choose our slice thickness, but I want to get into a little bit more on why that might be important. So if we look at a sphere that is contained within our imaging volume, for instance, and let's say the sphere has a diameter of about 50 nanometers. If we're acquiring this with X and Y dimensions of each voxel of 10 nanometers, so it's 5 voxels by 5 voxels, and our slice thickness is also such a way that our voxels are separated by 10, our slices are separated by 10 nanometers, we get equivalent resolving power when our voxels have the same X, Y, and Z size. So it's going to be 5 voxels in X, 5 in Y, 5 in Z. So this sphere is going to appear to be 50 nanometers by 50 nanometers by 50 nanometers. However, let's look at the case where we have anisotropic voxels, meaning that our slice thickness in Z is not the same dimension as our X and Z components of the image. So again, we're looking at our imaging plane here. We have the X and Y of the voxel set to 10 nanometers. But if our slice thickness is set to 20 nanometers, again, our sphere is 5 voxels in X, 5 voxels in Y. So it looks like it's 50 nanometers by 50 nanometers. But in this Z dimension, it looks like it's either 2 or 3 voxels. We have to make some sort of decision on that ourselves, meaning that in the Z dimension, it looks like it's 40 nanometers or 60 nanometers instead of the 50 nanometers that it actually is. So when we use isotropic voxel sizing, we get equal resolving power in all dimensions by choosing a slice thickness that is equal to the pixel size. And that tends to give us more accurate quantification of our features, or at least consistently inaccurate quantifications if we're looking at features that are smaller than this. So we always want to use a slice thickness that is equal to the X and Y dimensions of our pixel to be able to avoid distortion of our features of interest in 3D volume. As well, once we've segmented our data, or we've acquired our data, we've registered our data, we've filtered our data, and we've segmented our data, we can do all sorts of awesome rendering tools. Again, if you're working with Amira Aviso, you're working with Fiji, you're working with Dragonfly, each has their own capabilities for stuff like this. So we can take that instance segmentation and we can partition it and color features based on their particle size, for instance, or we can make awesome 3D videos like this, where we can actually rotate the volume in 3D to get a full idea of what's happening within the sample. We can slice through our sample digitally to be able to see what's happening on the inside. And we get all sorts of important information as to what's happening on the inside of our 3D volume. So lastly, I just want to quickly talk about what we have available here at CCEM and what FIBs we have that are able to do tomography. So if you're considering FIB-SEM tomography at CCEM, there's 3 main microscopes that we have that are able to do this. 2 of ours are Thermo Fisher Helios 5s. The first of which is our Plasma FIB UXE. So this is equipped with a xenon source. This is best applied to larger volumes, and it's capable of doing both edge and interior tomographies. We have our Thermo Fisher Helios 5 UC. This has a gallium source, which is great for doing high resolution volumes, small volumes. And again, we can do both edge and interior tomographies with this microscope. And we have our Zeiss Crossbeam 350 system with the attached laser module. So this is great if we're doing interior tomographies at high resolution as well. And it has some interesting add-ons that are that can really make your life easier for 3D imaging. So on our PFIB system, like I said, the ion source is using a xenon ICP, inductively coupled plasma. We have a number of detectors that can detect both secondary and backscatter signal. The tomography software we use for automated acquisition is AutoSlice-and-View. And it's important to note that this microscope has detectors for both EDS and EBSD, meaning that 3D EDS and 3D EBSD are both entirely possible within this machine. As I mentioned, we can do edge and interior tomographies, and we're in the process now of setting up our Noble Dome air-free transfer system, meaning that we can go from glove box to the specimen chamber direct without having exposure, without exposing our samples to air. And the main advantages of this microscope is that we have higher ion currents available, up to 2.5 microamps, meaning that if we want larger volumes, this is the microscope for you. With the xenon ions, we also get slightly faster milling rates at these higher currents, and we can acquire backscatter and secondary images. On our Zeiss crossbeam, for instance, we're working with a gallium LMIS source. We have detectors for both secondary and backscatter imaging. The 3D automated software is what's called Atlas 3D. We can couple this with laser ablations. We can rapidly prepare sites from removing millimeters of material in some instances to be able to cut to a feature of interest. This is equipped to handle interior tomographies. And with this laser module and the cryo accessories that we have for this, it makes it quite a robust machine if we want to do precise milling of smaller volumes. The Atlas 3D engine makes it very easy to transition from our Zeiss XRadia XCT system. So we can go direct from XCT to FIB to be able to effectively zoom in on our region of interest in 3D. So from the scale of millimeters all the way down to a scale of a few microns. And in this microscope, we have capabilities to do both backscatter and secondary. And our last microscope is the Helios 5 UC. Again, this is another gallium LMIS source equipped with detectors for secondary and backscatter signal. It also uses AutoSlice-and-View software, but if we want to do edge tomographies with a gallium source, this is the microscope for you. Again, we have precise milling, it's capable of high resolution imaging, and this is going to get us the best fidelity in small volumes if we're using that form of edge tomography. So with that, I'd like to wrap up. I'd like to thank you for attending today, and I'd be happy to welcome any questions.